Good afternoon. So my talk is about gas-grain interactions. So the title is a bit cryptic. Actually, it's a shortcut of the outcome of a study, laboratory study of the sticking coefficients of ice on small grain analogs. So very simply put, grains are everywhere in space. You know, there are small dust particles made of silicate, and olivine for us is an analog, and they are also made of carbon. Their size is in ISM below a few hundred nanometers, and their temperature is around 20 K. So with time, there is a accretion of the ice layer that actually made by atom recombination that react together and forms molecules. And this ice layer is mainly made of water and smaller molecules like CO2, CO extra. And if you want to take into account those gas-grain interaction, you can use an accretion formula that collisions between gas species and grain. It includes the gas density, the number density of grains, their size, and you can see that they are considered spherical, but you can complexify the size distribution, and also the velocity, it's temperature of the system. And there is a prefactor, say, which is the sticking coefficient. It's can be reduced to probability. It's between 0 and 1. So 0, it means that after collision, the gas phase species bounces back to the vacuum, to space. While when it is 1, it means that the atom remains stuck on the grain and then can react with its colleagues. So in terms of surface science or modeling, the sticking coefficient is also the number of adsorbed species over the number of available sites per surface unit. So usually S is taken as unity by astrochemists, modelers, and indeed, so far experiments have shown that this is the case. For instance, this one has been published in 2016 by Vidali's group. So you can see the sticking coefficient of CO, CH4, CO2, and almost H2 are close to 1, and drops at various temperature depending on the species. And this is called the snowline temperature. This is temperature at which the species can't remain frozen on the grain. All the experiments that have been done so far has been recorded on flat surfaces like this one. And it was a nice surface condensed on a copper plate held at the indicated temperature. And the question was, and that's usually, does the size plays a role in the sticking coefficient? So for this, we have developed a new method for measuring the sticking coefficient using an old technique, that's X-ray photoelectron spectroscopy. On this experiment that is called the SUMO, it is located at the Centre Interdisciplinaire de Marseille. And XPS allows to monitor the growth rate of ice on any kind of substrate. For instance, in a typical experiment, we set 2 samples on a transferable sample holder, that's pictured here. A graphite plate in that case. Okay. Along with carbon nanoparticle film. Okay, they are also graphitic, but they are very small, 20 nanometer in size, as shown by this nice electron micrograph here, and you see that they make small aggregates, bigger aggregates of those nanoparticles. So typical XPS experiment provides us with a substrate signal. In the carbon case, we have a carbon peak at 285 electron volt, and an oxygen peak that corresponds to that increases, which corresponds to the growth of the ice layer as function of the water exposure I've forgotten to say that we keep those substrate at low temperature under ultra vacuum, and we expose them to a flux of a control flux of water or CO2. So the ice grow on top of the surface, and this fingerprint of the ice layer grows together. So the data analysis is very simple. We just plot the intensity of the oxygen 1s peak and the intensity of the carbon peak as function of the water exposure or CO2 exposure. And as you can see, this is the growth rate actually. And you can see that it's lower for carbon nanoparticle than it is for graphite. And this means that for the same water exposure, you have less ice on the substrate than you have on the carbon plate, on the nanoparticle than you have on the carbon plate. And we also use the gold foil for reference, for which we check that the sticking coefficient is equal to 1 using infrared spectroscopy. This difference is solely due to the sticking coefficient. So in this paper, we have published the sticking coefficient on variety of substrate like olivine and macronic particles of olivine, carbon, graphite, then macroparticles and nanoparticles of carbon. We use the gold foil as a reference, and we also use two surfaces that has nothing to do with astrophysics, but that just extend a set of data, namely TO2 and I2O3, and the nanoparticle counterpart to see if there are differences between the substrate, flat and in particles. So here are the results. So we have plotted the sticking coefficient, so between 0 and 1, as function of the size in a logarithmic scale. So we have, by convention, defined the flat surface as 1 centimeter in size, and then here we have some micronic particles and say nanoparticles. Yeah. So for gold, the sticking coefficient of water is equal to 1. But you can see that already on other surfaces like graphite or olivine, the sticking coefficient is below 1. And for instance, for graphite, it's 0.4. This is also what has been found by other groups in the past. And when you go to smaller surfaces, you have a strong decrease of the sticking coefficient down to 0.1 for carbon nanoparticles. Okay. So it's a factor of 10 lower than the conventional value of 1. We also wanted to know if the nature of the adsorbate has any effect. So we have studied CO2 because it's a molecule that has no dipole moment as water. And unlike water, it's also a molecule that can't make hydrogen bonds with other molecules. And basically, we have the same results. The sticking coefficient of CO2 is a bit smaller. It is, for instance, on carbon nanoparticle as low as 0.04. And it allows us also to study the sticking of CO2 on those surfaces pre-covered with water ice. So in order to model the icy grains in space, we so pre-recovered the surfaces with a thin ice layer, thin enough to keep the morphology size of the films, but thick enough to cancel the chemical identity of the surface that can play a role. And I have reported in that figure the case of TiO2, for instance. So if TiO2 is covered with ice, TiO2 water ice, so you see that the sticking coefficient of CO2 is close to 1. So as reported previously by Vidali and any studies that have been done so far on this issue. For ice, that's not that's porous. Actually, the sticking coefficient is a bit lower, and this was also reported by I think Jennifer Nobel and Ellen Fraser a long time ago with infrared spectroscopy. Porous ice condenses less CO2 than non-porous ice. And for semi-chronic particles, so we have an effect of the ice layer that also enhances the sticking coefficient. But what is noticeable is that for nanoparticles, actually, whatever if it is bare or covered with ice, the sticking coefficient is the same, which means that surface chemistry doesn't matter for the sticking coefficient. So the essence of this effect is to be found in an old paper published 30 years ago by Victoria Bush. She has computed an ice nanocrystal and shown that for hydrogen, the adsorption potential, we are talking about physisorption or co-adsorption. In that case, there is no chemical bond between the species and the surface. Actually lie on the crevices of the nanoparticle and not on the convex part. So it means that's kind of capillary condensation or Kelvin effect at the nanoscale. Convex part are less absorbing than concave part. Okay, so you can imagine that on a nanoparticle, the convex part are majority compared to the concave part or flat part. So that's why the sticking coefficient is very low. Of course, in space, grain can grow in more evolved region. It's not an isotropic growth of the small grains. It's rather an agglomeration of small grains. So like this model of Anthony Jones and Nathalie Izard. So, and that fits well with what we know for interplanetary dust particles that are made with an inner structure made of small grains. And if you look at the transmission electron micrograph of the nanoparticle of carbon nanoparticle we have studied, actually they are bigger than the primary particle at 20 nanometer, but in fact they are 100 or more nanometer in size. And in fact, we believe that the sticking coefficient of a big grain is that of the small grain that make them, rather than the sticking coefficient of what is important is the size of the primary particle and not the size of the. Last important result, I think, is the fact that when you warm a flat surface like gold or graphite onto which you have condensed water ice, or graphite microparticles or nanoparticles, the disruption temperature is the same. It means that even if there is less water condensed on it, the binding energy is the same. So it means that the snowline temperatures do not depend on the size of the grain. So in conclusion, we have found that the sticking coefficients are not very different, are not very dependent on the nature of the molecule, dipole moment, hydrogen bondings. We have found that indeed it is close to 1 on bare gold on flat ice fields. It's closer to 0.5, 0.4 on the favorite laboratory astrochemist substrates like graphite or living, and also on icy grains that are, say, semi-chronic in size. But iced for bare grains, it's closer to 0.1, between 0.1 and 0.3, and for nanograins, it's whether they are bare or icy, actually the sticking coefficient is very low, 0.1 for water, 0.04 for CO2, and the grain composition doesn't matter. So astrophysical implications are that, first of all, S is not equal to 1. So it means that gas-grain reaction, not rates, but rather yields, must be revised because, of course, if you have a B atomic reaction on the grain surface, so you have to multiply this by the sticking coefficient of the two atoms. So it means that 0.1 multiplied by 0.1 is 10 to minus 2. So the yield is much lower than you would expect with S equal to 1. And the correction rate also must be revised. What else? Also, because the sticking is difficult, you can have a coexistence of gas phase and grains that are at temperature lower than the snowline temperature, because you need a lot of collisions before all the species are frozen out, which means that when you use a snowline temperature as a thermometer, if you don't leave enough time for say, washing out all the gas phase, you might have this coexistence of a gas phase species with very cold grain. And last thing is that the snowline temperature, however, is independent of the size. Thank you.